any further ado, I'd like to introduce Seth, who will be presenting on driving forward with Android drivers, exploring the future of Android kernel hacking. So please give a warm Shmoocon welcome to Seth.
Hey, how's it going? My name is Seth, as you found out already. Let me put this right here. Today we're going to be taking just a brief glimpse into the future of what Android driver hacking might look like, and what we might see for Android kernel and local privilege escalations in the future. Just as a brief sort of agenda on what we're going to be talking about, I'll briefly discuss who I am. Then we've got sort of a couple fun segments here. We've got enumerating the attack surface. I'll explain how I went about the process of finding different Android drivers on Android phones, developing different techniques for discovering them and looking for interesting ones. Then we'll discuss some of the attack surfaces that I looked at and some of the bugs that I found. And finally, we'll take one of those bugs all the way to root. And then at the end, there will be a live demo against my better judgment. My name is Seth. You can find me on Twitter or X. I'm an information security engineer at Google Project Zero. I primarily look at Android and Linux kernel research, focusing mostly on local privilege escalations. If you haven't heard that term before, I'm trying to get to root without using a password. One fun fact about me, particularly in this field, is that I love to turn bad bugs into good exploits. I love to find stuff that's particularly difficult to exploit and find a way to manage it anyway. I really live for good, innovative exploit strategies. So let's talk about Android drivers. What are Android drivers? They are something that is used to facilitate interaction between user-landed hardware devices. Basically all Linux uses drivers at some level. Even if you're using a VM, it's still using drivers. And it basically, every time that a user-land process wants to talk to a piece of hardware, it has to go through a driver of some sort. And all those drivers are sort of hosted inside of the kernel. They are a very well-known kernel attack surface. Particularly on Android, we've seen a lot of previous research in GPU drivers. That is Mali, Adreno, PowerVR, et cetera. We see that both in the wild and from the security research community. But GPU drivers aren't the only piece of hardware, or GPUs aren't the only piece of hardware that have drivers on the system. Other chipset components also have drivers. That is, by chipset, I just mean like all of the other different hardware pieces and chips that are on an Android phone. And they're usually accessible to userland in some method. Usually that's via character device files, usually in either devfs or procfs, also known as the /dev and /proc folder. And there's been a lot of research into GPU drivers, but not quite so much research into other chipsets drivers and what sort of bugs we might see from those sorts of drivers. And so I wanted to sort of look forward into the future. Right now, GPU drivers, that's sort of the bleeding edge. But what's going to be coming after that? If GPU drivers, if one day we enter this idyllic land where GPU drivers are perfect, where are attackers going to start looking for bugs next? What sort of other drivers might be available, and how can I get ahead of them? So I really wanted to dive forward. What other drivers are there on an Android phone? And to do that, I needed to enumerate the attack surface. That is, find all of the Android drivers on the Android phones. I developed a couple different techniques, some of which are really obvious, some of which maybe not so obvious, to find these drivers. The first one is file system searching. This is the most primitive version of it, and it works very well. And that is just to enumerate all the files in the file system, looking for interesting drivers. Another technique that I used was source code analysis. That is actually looking at the Linux kernel source that Android phones have published with them. That's a whole other story for another day about how to get that, but there's plenty of resources online to be able to acquire that. All above board, of course. And you can find calls to proc create or device create or et cetera, other kinds of calls that are used to actually create create those drivers or create those files on the file system that expose those drivers. And we also looked at SE Linux policy analysis, where I actually evaluate the sort of policy permissions of SE Linux to identify things that the developers expect userland to be able to access. So let's talk about file system searching first. This is the obvious one. I'm just going to use file system enumeration tools to look for interesting files and folders on Android phones, also known as using find and ls. Then I just check permissions and accessibility, and I do this using cat. Super fancy stuff, I know. But it's really effective. There's some pros to this. It's really easy. It's very real. There's a low false positive rate. If I can see the file and I can access the file, then it's a file, and it's potentially an interesting attack surface. There are some cons, though. It misses files in unsearchable directories. We'll talk about that a little bit later in like a slide or two. And also, it can be a little bit difficult because you have to be cognizant about what SE Linux context you're accessing the file from. There are occasionally files that can be accessible from some like debugging contexts, but then not actually from an untrusted app or vice versa. And that matters particularly when you're trying to find interesting attack surfaces. And it's also really tough to evaluate attack surface complexity quickly. So like once I find a file, I still have no idea, it's not immediately apparent how much code or how much of a driver there is backing up this thing. The complexity of that driver or whatever's backing that file in the kernel is fairly unclear. So there are some pros and cons to this technique. The other technique, well, here's an example of just seeing this in practice. You can see I use find. I'm listing all the files in /dev. And then I try catting a whole bunch of them. And you can see that a couple of them throw out permission denied, but one in particular throws out operation not permitted. That's kind of a misnomer. It doesn't mean that I couldn't access the file. It actually means I could access the file. I didn't get a permission denied error. Operation not permitted is something that the kernel is throwing after I've opened and accessed the file. So in this case, I've actually been able to open Mali0. And Mali0 is the GPU driver, which we've discussed before. And my goal is to find other files that may throw something like this. We're specifically looking for something that isn't permission denied. So another technique I used was source code analysis. This technique was also quite fruitful. We're basically examining the source of the Linux kernel itself for that Android phone, looking for character device creation function calls. And then once I find those, I find the file if it exists on the device. And then I'll just check for if it's accessibility. Use cat. The real benefits of this is that it ignores outer directory permissions and that the attack surface's complexity is highly apparent. So I get to scroll through the code and be like, oh, wow, that looks like an interesting driver. Where is it supposed to be created? And then I can immediately sort of jump right to the risotto in terms of finding the interesting stuff. And I don't spend a lot of time finding boring drivers that I can see but aren't actually interesting, like /dev/null or whatever. I don't waste my time on stuff like that. Cons, it doesn't tell you a lot about the permissions on the files. So like, I'll see a driver be like, wow, that looks super interesting. I want to hack on that. And then go and look on the phone and be like, oh, it does exist, but like, I can't access it for reason X, Y, or Z. So you get lots of false positives. And it can also be quite difficult to tell whether the driver is actually being compiled into the device. You really just need to check each one manually to see if that's true. But here's a great example of this being of seeing this in practice. This is from a MediaTek chipset phone. I could see from the source code that there was this directory called perfmgr, and then there were some files being created inside of there called using procreate. Perf-ioctl, EARA-ioctl, et cetera, et cetera. You can actually see on the right side that when I try and access this directory from an untrusted context, I'm unable to do so. However, if I try and access the file itself, either by listing it in the directory or by catting it, or I actually just stat it, is what ls-l is doing there. Or if I actually try and cat the file, you can see that it is in fact accessible. So this is something that if we were just used basic file system enumeration, it would fail. It could not find this. But by looking at the source code, I was able to find this and evaluate this attack surface. So it's a very odd permission setup. I have no idea why, but it exists empirically. The final technique that I used was SE Linux policy analysis. Discussing SE Linux is perhaps a little bit out the scope of the talk, but like one brief sentence is that it just allows for robust and granular permissions decisions at runtime based on process context, and it does this using a policy file that is loaded into the kernel at startup. And those policies usually reflect what the developers intend to be accessible. So by looking at the policies and looking for cases where files or where certain file contexts are readable or openable or ioctolable from an unprivileged context, it sort of betrays that which the developers are expecting me to be able to access. And it suggests that I should do greater investigation into those files to see if they're interesting. I can look at the SE Linux policy from the device using a program called SE Search, and I can look for those interesting device files. Then I have to find the location of that file, which can be a little bit tough because nothing about the SE Linux policy betrays where the file might actually be. Well, maybe a little bit, but it's not immediately clear, that's for sure. But hopefully, if we can achieve all that, then we can get profit from that. Permissions on the files are immediately apparent is the really nice thing about this technique. And if I see it in the policy, the file almost certainly exists, which is also very nice to know. But once again, just like file system enumeration, the attack surface complexity is completely unclear, and it can be quite difficult to find the files on the device. Oh, there used to be another slide in here where I showed an example of. Okay, well, there was at least one bug that I found with this technique that was a bug in the Edge TPU on Google Pixel phones, on the Google Pixel chipset. Oh, I know, that slide's like just 2 slides later. I know where I'm at now. Okay, so let's talk about the bug hunt. So first we have this device list. I looked at 3 different devices, the Google Pixel 7, the Xiaomi 11T, and the Asus ROG 60. 2 of them were MediaTek's, one of them was a Google Tensor chipset. I wish I could say that I was like trying to create some sort of, thorough evaluation, a survey of all of the major chipsets on the market, but that's not true. It was just what I had on my desk. So looking at the Google Pixel 7, I found fairly few accessible device drivers from the untrusted app SE Linux context. For the record, untrusted app is just the SE Linux context that most, if not all, of the files, or most, if not all, of the apps running on your phone are running under. So this is sort of the context that particularly matters. There are caveats to that, but I'll just leave it at that for now. The GPU was the big exception to this fairly few accessible device drivers, but SE Linux identified one particular other device of interest. It was this Edge TPU device, and I could see from the SE Linux context that I was able to ioctl this device, I was able to read this device, but I wasn't able to open this device, which is like super weird. And sure enough, this file does exist on the phone. This driver is on the phone. What's going on with this driver? I wasn't quite sure, but so I did a bit more research trying to figure out what's going on, and the answer is that there's an allow list of apps that are allowed to access this device, and an allowed app actually has to ask a service process for the file descriptor, and the service hands it back. So there's this entirely userland contract where an untrusted app will go and ask another higher privileged process, hey, can you open this file for me, and then hand me the file back, and that's like totally okay. But most apps aren't on this list. There may be some notable, interesting exceptions, like Google Meet and stuff, but for the most of the time, it's not accessible from your typical untrusted app. I did find one bug in this driver, and I reported it as CVE 2023-35645. You can go take a read if you want. I don't think it's all that interesting, really, though. But the MediaTek attack surface yielded some much more interesting drivers in there. Right away, I could see that there was more of an attack surface on MediaTek devices than there was on the Google Pixel devices. I found several different sort of drivers of interest. GED, which we're going to discuss a little bit later because there were some great exploitation primitives in here. The MTK JPEG driver, and also this perfmgr driver that I talked about earlier. The MTK driver, JPEG driver in particular, stood out for me. It was odd because you could not access it from the shell context, but it could be accessed from an app context. And here you can see I try and access the file from the shell context. I fail. I change to an app context, and then I am able to access the file, which is very odd. I decided to do a little bit more research into what this driver and the source inside of it might look like. So the first investigation was like, what is this driver? Why does it exist? It's the MediaTek JPEG driver that the JPEG decode hardware uses. There's basically JPEG decode hardware present in the MediaTek SOCs, and this is sort of the driver that sort of backs that hardware. There's a couple things that the kernel does for this. It sets up memory mapped registers. It maps DMA memory into the decoder, and then it can start decoding by writing to a certain memory mapped register. And after decoding, an interrupt is sent back to the CPU to say, hey, I finished decoding. The JPEG decoding hardware sends back an interrupt. And so this JPEG decoding hardware is just used to accelerate decoding of JPEG, JPEG codecs. And there are 2 cores, which means that up to 2 JPEG streams can be decoded simultaneously. I found the driver implementation. There's actually 2, but the one that I was most interested in that backed to this file, mtkJPEG, was present in drivers MISC MediaTek JPEG. And inside of this, I only found 3 ioctl calls, so 3 really obvious ways to interact with the driver. That was the JPEG DEC ioctl hybrid start, the hybrid wait, and the hybrid get progress status ioctls. And so the hybrid start is simply used to start a JPEG decoding operation, and then once the decoding operation begins, the userland process will call hybrid wait, and then just wait for the interrupt to occur to get sent back. So there's sort of like this. It's just basically these 2 ioctls. There's one other, but it's uninteresting. There's basically, for at least this talk, but there's basically 2 ioctls that are used, and they just bounce back and forth. Start, wait, start, wait. So let's take a deeper look into these ioctls, or at least 2 of them. Here is JPEG DEC ioctl hybrid start. If this looks like a lot of code, that's okay. You don't have to understand all of it. There's just a couple things I want to note. First is that you can see here that it gets userland parameters. That is where sort of untrusted input enters into the system. We also see this this code here, hybrid DEC lock, which is choosing and locking a core. As I noted, there's 2 cores, which means 2 streams can be decoded simultaneously. This DEC lock function has to choose which core it can access based on what other threads on the system are doing. So if another thread and another process chooses to decode a stream, then they can't both decode with the same core simultaneously. So it just has this function has to make sure that that doesn't happen. And we'll talk about that function a little bit more. Then we have this function hybrid DEC start that initializes and starts the core. And then we have a function which presents the outcome of that start to userland. And finally, we have this code at the bottom that, like, if for whatever reason JPEG hybrid DEC start doesn't start properly, will unlock the core if we failed that startup process. Here's the JPEG DEC ioctl hybrid wait. There's really only 4 things that are important here. First thing to see is that it confirms that the core is locked before doing any more additional work. Then it just checks to see if the interrupt has fired. If it hasn't fired, it waits for that interrupt to complete, and finally it unlocks the core. This is actually where bug number 2 is found. You can't see it in this example because this is the patched example, but on certain maintained versions of this code, this check was actually skipped, and that led to out-of-bounds read and write for older supported kernels. And I reported that one as well. We'll discuss that one a little bit more, but not too much. One thing to note, though, is that, like, I've highlighted it with this red rectangle here. There's this DEC hardware locked check, and then there's this JPEG DRV hybrid DEC unlock at the end. It seems that these 2 things are sort of playing, have a relationship between the 2 start and the waits. The start is supposed to lock the core, and then wait is supposed to unlock the core once the operation is completed, which makes sense. So yeah, there's this basically these 2 things are working in tandem. Let's look at how this function works a little bit more in depth. So you can see that it has this sort of mutexing to protect it, and it's just checking under the mutex if a core is locked, and if it is, then it locks it, or if it isn't, then it locks it, and if it is, then it checks the next core, and if it can't find a core, then it'll fail out, and if it can, then it'll lock it and exit out and release the mutex. That's important. We also see sort of a similar sort of reverse behavior in JPEG and the unlock function. So if it's not locked, first it takes the mutex. If it's not locked, then it just leaves. If it is locked, then it unlocks it, and it also frees a whole bunch of data previously associated with that core. That was data that was initialized during the start routine. And once again, I've noted that these are mutext. That is, these functions have been designed so they can't race with each other, which is nice, but really it's only the blocks in red that are protected. Nothing else is protected except for these blocks. Any of the other sort of parts of these ioctals can run simultaneously. So in practice, what does this look like? It means these two sort of like red areas are protected. Nothing else is. And just like start and hybrid wait, we see that the bottom is protected. Right at the end, it protects this one call to unlock, but none of the rest of it is protected. Right away, we see a correctness issue because you can see it checks deck hardware locked to see if the core is locked, and it checks that outside of the mutex. The state of that core could theoretically change at any time. So let's put it together. We're going to have two threads. One is running start. One of them is running wait. So the first guy who's running the start ioctal is just going to lock a core. Great. Thread B, which is running wait, is going to check to see if the core is locked, which it is, because I just locked it on thread A. Excellent. Now thread A is going to run JPEG DRV hybrid deck start. And that's going to fail for whatever reason. And because of that, it's going to enter the unlock, and it is going to unlock the core. Right away, we have a correctness issue, because now thread B is running on an unlocked core, which is never supposed to be an intended behavior. Thread B, nevertheless, is going to check to see if the interrupt fired, which it won't, because the core was unlocked and isn't being used. And then it will enter a timing out wait, waiting for the interrupt to fire, which it never will, because the core isn't being used. And that wait will go for like 3 seconds. Finally, thread A will exit back to userland from the start operation, and then I'm going to have it enter the start operation again. It's going to lock the core again. And now thread B is going to finish its wait, never find the interrupt, be like, I don't know what to do, let me just unlock the core, and it's just going to unlock the core, even though thread A is currently in the midst of trying to initialize the parameters that thread B is simultaneously attempting to free. This is just arbitrary, like outright racy. I reported this bug as 32832. This was a race condition in that driver. You can go and view this on our bug tracker. So let's now discuss getting from those 3 bugs to root. I was trying to find one that was like really interesting from any sort of untrusted app perspective. Right away, that sort of disqualified bug number 1. It could only be used with an allow list, so I don't care about that. So instead, I was most interested in these other 2 bugs. The out-of-bounds read and write, it looks like it should be super exploitable. It's a deterministic out-of-bounds read and write at a controlled offset. That feels like it should be good enough. That feels like it should be strong enough to exploit. But there's a couple of things that make it quite difficult. One is that the array that I'm accessing out-of-bounds is in the globals. So I couldn't really control anything about what was behind or in front of this array. The read was also very complex. It was reading entire wait queue struct, and it had to meet certain criteria in order to trigger the write at all. And the write itself was minimal and very, very difficult to control. I could write basically 0 and 1 and some stuff, and that was it. I did sort of develop this technique. I found that by overlapping the out-of-bounds wait queue struct with another wait queue in the globals, and then hitting a tiny 2-instruction race that I made easier with a cache miss plus a preemption, I was able to convert this primitive into a racy write of 4 bytes of 0 to a static stack offset in another process's kernel task stack, which is a great primitive, I thought. And so I actually wrote a tool to try and turn a backtrace into a pictographic of the kernel stack and have a depiction of where the write occurs in the task stack relative to the function frames of arbitrary system calls. And if that sounds really complex to you and you didn't understand any of that, that's okay. I couldn't find a way to exploit it anyway. But if this nerd sniped you, come talk to me afterwards, because I'd love to hear different theories for how this might be exploitable. Because I feel like it should be. It feels to me in my head like I should be able to exploit this, but I wasn't able to find a way. So I decided to turn to this other bug, this race condition, which we've spent quite a bit of time talking about already. Once again, we're having two threads. We're starting, we're waiting. There's going to be a locking. This lock is going to occur. Or it's going to check to make sure that it's locked. Then we're going to unlock the core. We're going to enter this interruptible wait timeout that eventually is going to end. In the midst, we're going to exit from that ioctl, enter the start ioctl again, lock the core again, and then thread B is going to unlock the core at the same time that thread A is trying to initialize the parameters. And this is what's racy. So if we actually look at these two things that are racing simultaneously, we see that basically the one on the left is initializing all of these parameters at the same time that JPEG DRV hybrid deck unlock is trying to free all these parameters. And one particularly interesting behavior that you can do, depending on how you want to, you can basically overlay these functions however you want and find which version best suits your sort of exploitation strategy. And I found that if you just put the unlock completely before the JPEG start, then all of the freeing code will happen on the previously freed resources because JPEG hybrid DRV or JPEG DRV hybrid deck start hasn't initialized any of them yet. So if start ran one time before and initialized a bunch of those resources to something, and then unlocked the core and freed its access to those resources, and then later on we have this sort of weird race. And then start is going to run again, but unlock runs first. Then unlock is going to run on the previously initialized resources, and it's going to free those resources a second time. So I was particularly interested in those puts that we saw over here on the right side, the JPG DMA buff put, because those are based on file descriptors. We see right away that underneath that it calls DMA buff put, which underneath it calls fput on the DMA buff file itself. This is just basically a ref count that's supposed to be sort of in tandem with the starts ref count taking over on the other side where it calls JPG DMA buff get. But once again, we're calling put twice while we've only called get once. And this is just a double ref count decrement. And that's just, if anyone is familiar with ref count exploitation, that just means that this is straight use after free. The kernel tracks these struct files, objects via ref counts, and when the ref count reaches 0, the kernel believes the object is no longer referenced, so it is freed. But one of these ref counts is spurious. One of these ref counts wasn't supposed to happen. The object is, in fact, still referenced. Where is it referenced? It's referenced in the file descriptor table of the process, because that's where start got it from. So now I have a dangling struct file held to a file descriptor that userland can still access, which is a great primitive, by the way. Once again, we see here in the JPG DMA buff get that it's accessing the file from the file descriptor. Now attacker userland has reference to a file descriptor where the backing struct file has been freed. This is a great primitive. There are so many different potential ways to exploit this bug. One big issue that you might run into right away is that files in particular are allocated from a dedicated kernel slab cache. That just means that when you free a file pointer, a struct file, basically usually the only thing that's going to be reallocated in that space ever is another struct file. There are ways around this. The typical use after free strategy for replacing this with some other object type involves a little bit of complexity. You can either use cross-cache exploitation, where you free it back to the page allocator and then get another kmalloc slab cache to take that page and add it back into its own slab cache and then utilize that to sort of achieve a type confusion of some sort. And then there's also a technique where you just free it back to the page allocator and use the page allocator directly. Example, reallocating with pipe buffer pages to grab this page and sort of put, say, arbitrary data in that place. But cross-cache and all these techniques, they do involve a little bit of complexity, and there are some reasons to hope that some of these techniques might go away soon. There's been some mitigation sort of added into play in some sort of off canonical branches that are trying to resolve this issue. My colleague Jan Horn's research has also gone into trying to solve this issue and prevent cross-cache attacks. So I was interested to see, we're looking at the future. Is there some other way to exploit this bug that doesn't involve cross-cache exploitation? The answer is yes, there is some other way. Let's discuss this some other way. So when an object is freed, that internal data becomes stale, but it nevertheless remains set. With the small caveat, unless a certain kernel command line option is flipped on, which it usually isn't. That means that once an object is freed, the data remains the same as before it was freed, except for any heap metadata that the kernel decides to introduce, which there is some. There is a free list pointer that's introduced into the chunk when it's freed. They put it in the middle. There's really good reasons for that. You can talk to Case Cook about it if you really want to hear why, or you can go read his commits online. But they put the free list pointer in the middle of the chunk. But other than that, the rest of the object remains intact. That means that this struct file can actually still be potentially accessed in a sane way. File operations might be performable, et cetera. There's nothing stopping this freed object from being just used like the object still exists. In practice, if we actually looked at one of these struct files, they have a private data field that is used to reference some type-specific data. And normally in a DMA buff file, that private data points to a struct DMA buff. We can see in the DMA buff get caller that once it actually fetches the file from the file descriptor, it returns the private data field, and it casts that private data field implicitly to struct DMA buff. So struct files might come from a special slab cache, but struct DMA buffs does not. And when the file was freed, the DMA buff was freed as well. And that DMA buff can be reclaimed with a different type object coming from a generic kernel kmalloc slab because it was allocated from the general kernel kmalloc slabs. So when I free the struct file, I leave a dangling file descriptor pointing to that struct file, which also points to a free DMA buff because that DMA buff was freed at the same time. Then I reclaim the DMA buff without reclaiming the struct file. I leave the struct file free and I only reclaim the DMA buff memory. And then I can call DMA buff operations on the dangling file descriptor using this dangling file descriptor to access a freed struct file, which has a pointer to reclaimed DMA buff memory that comes from the general kmalloc caches. But wait, the astute among you might ask, that struct file could be reclaimed at any time. Something else in the system could grab it at theoretically any point it wants it to. And that means that the longer it exists, isn't it going to disappear? Nothing's stopping that from disappearing. You're right. In practice, at the speed that my exploit will run, this isn't really a problem that happens very often, but even if it were, we can avoid this by burying that struct file in the free list by freeing a whole bunch of struct files immediately after it. And by doing that, we can make sure that the allocator doesn't see it for a long, long time. So now I'm left with a couple questions. I've talked about reclaiming the DMA buffer, but I have no idea what I'm going to reclaim it with. And what operations can I call on that DMA buffer to achieve any sort of interesting primitives? Once again, now we're going to go back a long time ago and talk about the GED file, which I mentioned had some really good exploitation primitives, and two really good exploitation primitives came out of this file. One are GED GE buffers, and the other is GED DMA buff set name. And we're going to discuss both of these in depth. So first, let's talk about what the GED driver is. It's called the GPU extension device. I've quipped that it's the GPU exploitation device. It has in it an array of GE buffers, or basically with this driver, you can allocate an array of GED buffers or GE buffers. It's dynamically sized buffers. They're allocated in the generic kernel kmalloc slab caches. Their size is controllable. You can read and write the contents at will without freeing and reallocating those buffers. And of course, you can also free and reallocate them at will. And basically, this is the holy grail of heap sprays. It's controllable in size. You can control the data. You can read it and write to it however you want, whenever you want, without reallocating that memory. It's excellent. So once the DMA buff is freed, I'm going to reclaim it off that free list with a GED GE buffer. So now there's a type confusion. I have a GE buffer pointing to the same memory that someone else thinks is a DMA buff. The GED DMA buff set name is simply an alternative to another known canonical ioctl called DMA buff set name ioctl, called the DMA buff set name ioctl. The only real benefit of using this particular call as opposed to the normal ioctl, canonical ioctl, is that it doesn't do any SE/Linux inode checks on the file descriptor, because that'll crash on a freed struct file, but meanwhile, GED DMA buff set names will not. When this function is called, it will free a pointer to whatever previous name was in the DMA buff struct, or it won't free anything at all if it's just set to null, and then it will allocate a new name string. In the context of the fact that we now control this DMA buffer because we've reallocated with a GE buffer, what that really means is that we'll free an arbitrary pointer, and then we'll allocate a new name string. And that new name string will also be visible because it's in the GE buffer memory, which, as you might recall, we can read and write at will. Since the file descriptor still exists, we can also read proc self fdinfo n. That when we read the fdinfo of that file, it will call this function on the side, on the right side, which will call file count on that freed file, and that file count reads the ref count of the file. But once again, we reclaimed the entire DMA buff struct with a GED GE buffer. So when we grab the DMA buff from this file's private data, when we re-access that file through the file count, when we re-access that file through DMA buff -- file, it's actually accessing arbitrary memory that is the GE buffer. And that means I can set that file pointer that's used in file count to any arbitrary value I want. So in practice, I'm dereferencing an arbitrary pointer and printing an integer from an offset of that pointer. This is arbitrary read. As a recap, we now have some great primitives. We have an arbitrary read via fdinfo. We have an arbitrary free via GED DMA buff set name. And we can retrieve the fake DMA buff struct memory via the GED GE buffer read. So we can read and write the GED GE buffer at will, which means we can read and write the DMA buffer at will. We have an arbitrary read, and we have an arbitrary free. Now we just need an arbitrary write, and I'm done. If we can gain arbitrary control of the array of GE buffers, then we have a very nice read-write primitive, and we'll very easily be able to get to root. We can use our arbitrary free to free the GE buffer array and then reclaim it with a GE buffer. As a brief reminder on what the difference of those two things are, there is a GE file descriptor that has a GE file. That GE file references a GE buffer array, an array of GE buffers, and then inside of that are GE buffers themselves. And that GE buffer array is really just an array of pointers to GE buffers. If I can type confuse a GE buffer array with the GE buffer itself, I can then set the GE buffer array and the pointers inside to whatever I want. And then this GE buffer points to wherever I want. And because I can read and write it at will, because that's just the feature of GE buffers, I now have a really great arbitrary read-write primitive. We will be able to arbitrarily free this array if we know where the array is. So the next question becomes, how exactly do we find one? There are three different ways that GE arrays are sort of referenced. So the hierarchy is that the GE arrays are referenced by a file descriptor itself. Then file descriptors are referenced by a file descriptor table. And then file descriptor tables are referenced by a task struct. If we were to keep going down, we could see the task structs are referenced by the task struct list or whatever, but we're not going to discuss that today. This is enough. If I can find any of these three things, I will win. I will be able to access and free and find the address of the GE array, free it, and reclaim it with a GE buffer. So let's try and find one of these. There's a couple different ways to do this. The way that I found that was fairly straightforward is I found out that FD tables come out of the same generic kmalloc cache as the DMA buff name pointers that I can cause to be reallocated and freed at will with GED DMA buff set name. Because they come out of the same generic kmalloc cache, that means that I could potentially predict the location of an FD table. If I somehow have a DMA buff name address, then I free that DMA buff name associated with that address, and then allocate a lot of FD tables, reclaiming that DMA buff name address with an FD table. And by doing that, I've basically predicted the location of an FD table. It's sort of backwards from your typical sort of strategy where you reclaim and then find the address. In this case, I'm finding the address and then reclaiming with a heap spray. I can use GED DMA buff set name to place a new pointer in the fake DMA buff struct, and then I can read that fake DMA buff struct because GE buffers are awesome. And I can use that to get the name pointer. Once I have the name pointer, I can call GED DMA buff set name again to free the name pointer, and then I can reclaim the name pointer as an FD table with references to a GE FD with an array of GE buffers. So the FD table that I'm hoping to reclaim it with will have an GE FD in it, and that will have an array of GE buffers in it, and then I will be in business. Finally, I will use my arbitrary read to find the array of GE buffers. Then I will use my arbitrary free to free the array of GE buffers, and then I will reclaim that array of GE buffers with another GE buffer. So now I've really achieved the type confusion. I've turned an array of GE buffers, and I've reclaimed it with a GE buffer itself, and we've type confused that array with a real buffer. And then we just have profit. So in practice, here's a little chart that maybe hopefully makes it a little bit clear. On the left side here, we have got the DMA buffer struct file. As you may recall, this is free. It has been freed the entire time. It needs to remain free, otherwise my exploit crashes. Or actually, it won't crash now that I think about it. But nothing interesting will happen. Next, I have this DMA buff struct, which I've reclaimed with a GE buffer. There are two sort of major members in the struct that you should be aware of: the file struct that I'm using as my arbitrary read, and the name buffer that I'm using as my arbitrary free target by calling GED DMA buff set name. Here's my arbitrary read at the top, and on the bottom is my arbitrary free primitive. So first, what I'm going to do to explain the sort of strategy again, I'm going to set the name pointer. That's just going to set it to an arbitrary location, and I think it's kmalloc 32. I would need to check. Then I'll get the name pointer because it's just in the GE buffer now. Easy. And then I will free the name pointer by calling GED DMA buff set name again. And now I have a pointer to the active kmalloc slab, except that chunk is freed. Then I will reallocate that free name pointer with a file descriptor table. In practice, this is very easy. I just create a lot of new processes containing a GEFD using fork. Then I'll read the FD table, and I'll be able to find the GE buffer array address. Super easy. I just call procself fdinfo-n after setting the file in the GE buffer to an arbitrary location. The arbitrary location in this case being the location of the name buffer. This is sort of a description of how that's going to work in practice. We've got the FD table, we've got the GE file, we've got the GE buffer array, and underneath that we have the GE buffer. This is just the references I have to go down in order to find this file. And in practice, what I can do now is since I know where the GE buffer array is, I can call GED DMA buff set name after setting the GE buffer array as the name in the GE buffer, or the DMA buff, depending on how you want to think about it. And then that will arbitrarily free the GE buffer array. Then I reclaim that GE buffer array with another GE buffer. Now I have two GE files, a blue one and a red one. The blue one has a completely canonical GE buffer array, and what to it is a completely canonical GE buffer. But the other GE file thinks that same thing that is the blue file's GE buffer is its GE buffer array. And so now the GE file, the blue GE file, can set the GE buffer array values to whatever it wants it to be, and the dereference chain for the red GE file will access any location memory the attacker wants. And then because of GE buffers, I can read it and write it at will. This is a great arbitrary read and write. The benefits of doing it this way: it's very repeatable, it's very reliable, and it's fast, and it's in practice quite easy. Finally, the goal is to get to root. That's what we're all here for, after all. To do this, I just write to my own process's cred struct to set the UID to 0. Because of Android, I also need to set some capabilities as well. And finally, using my arbitrary write, I write 0 to the SELinux enforcing bit to switch SELinux to permissive mode. And finally, I will exec lb system bin sh, and we're all done. I have a root shell. What are some good conclusions from this sort of research that I did? One is that Android kernels remain a really ripe source of bugs, and they also serve as a good place to find exploit primitives, for example, heap sprays. And we also see that, and this is something we've noted for a while, is that there tends to be pretty questionable code quality outside of Linux mainline. There can be questionable code quality inside of Linux mainline too, but particularly outside, we see that it's not getting as much research, it's not getting as many eyes on it as we'd really like them to, and so there are still significant and serious bugs coming out of these. Just generally, the code quality in these is just not as good as we would like them to be. And also, there are some really effective exploit techniques outside of just cross-cache and page allocation reclaims. And you don't always have to reclaim a use after freed object for it to be useful. Sometimes using it while it's free is just as good as anything else. Great, so questions in demo time. I'm gonna run the demo off my phone really quick. My exploit is maybe I don't know, 50% reliable. So it's a great candidate for trying on stage. In practice, that means it will crash the first time I run it 100% of the time, but we can hope. And if this does crash, then I'll just start taking questions while we wait for the phone to reboot. This is the process where it's trying to hit that race that I was talking about before. It needs to take a little bit because it doesn't always hit it immediately the first time. And pretty sure the phone just crashed. Yes, it did. Look at that. We are 1 for 1. So now is a great time for me to take some questions while this phone reboots. Questions? All right.
How long did it take you to figure out this entire exploit chain?
In terms of like actual amount of time, I spent from like point A to point B. It was somewhere in the range of 7 months or so. But the amount of time I actually spent working on this in particular is significantly less, probably in the range of like 3 to 4 months, more likely.
And would you say this is your most complicated exploit you found to also create?
No.
Okay.
Not
Thank
even
you.
close. And that's all I can say about that. Actually, if you want to see a really cool exploit that is public a while back, you can go look at the null pointer dereference exploit that I wrote a while back, where I actually changed a null dereference in the Linux kernel into an exploit, which shouldn't even be possible nowadays, but it totally is in practice. All right, so I would love to take other questions, but let's actually try and get the exploit working this time. Okay, so now I'm in the context, and by the way, I'm doing this backwards. Literally, I can see the screen just backwards, so hopefully the things on the terminal are working correctly, and I'm just typing from memory because I can't see it. So we're going to run the exploit again. I can see it's working. 50% likelihood. Oh, look at that. You can see I'm root. And also that SE Linux is in permission mode, or in permissive mode. And now the phone's just crashed, so that's the demo. Thank you. I have about 5 minutes if there are any more questions. Yes. Oh, some of the really questionable code quality in these drivers it's really astounding. Yeah, I mean, like you'll see stuff like int uint 8 30 or uint 32 variable name. They just named the variable uint 32 underscore something, but it's actually a signed integer. It's like, I don't understand. How do you do that? But yeah, I'd say in that I was like, wow, I've never seen that one. That's really creative. All right, any other great questions? I see one back here.
Did you have source for the MediaTek drivers?
I did have source for the MediaTek drivers. It's available online. You can access it. It's just available via GPL. That's all the questions I'm going to take now. If you want to come find me in the hallway, I'll be out there. I'm going to vacate the stage quickly. They had something else they wanted me to say, but I've forgotten what it is, so good luck.